Hi, my name is Jules Blok, and I'm the engineer in charge of the OpenXR integration in UE4. So before we begin, let me summarize what the talk is going to be about. The talk assumes you're already familiar with VR development in UE4, because most of that isn't going to change with OpenXR. And we also won't go over the entire specification, because a lot of details won't matter to you if you're just building your project. But if you are interested in every little detail of the specification, there are some very interesting talks by Brent Insko, the chairman for the OpenXR group at SIGGRAPH, where he talks about the entire specification as a whole. So why should you use OpenXR? OpenXR serves two parties mainly. On the one hand, you've got the hardware vendors who want to develop new hardware and run the games on that. And on the other hand, you've got developers who want to run their games on as wide a range of devices as possible. So first, the hardware vendor. If the hardware vendor releases new hardware, they have two options. They can either go through an existing runtime like Steam VR and try to fit that to their hardware, or they can make their own runtime and try and convince game developers to implement support for that runtime. On the other hand, you've got the game developers who don't want to spend that much time on implementing support for every single runtime that's out there in the market. So how can we empower the runtime to do as much of the porting effort for the developers as possible? This is also important because the dev teams might not actually exist anymore for the game that we want to port, because dev teams are temporary, but their games will last forever. So just as important as having an open standard is who owns this standard. So in the case of OpenXR, it's the KHRONOS group, which is a consortium of companies all working together to develop these standards and update them with various features. In such a consortium, every member has an equal vote. So there's no one company that is more in control of the specification than others. If you're familiar with rendering, then you might already know this group from standards such as OpenGL and Vulkan. So let's look at the current state of the VR market. We've got a ton of different runtimes, each working on some devices. Some runtimes run on more devices than others. But if you would want to support all these different runtimes, you would need to enable at least 4 plugins in the engine. And without a single interface to target them all, it's not possible to consolidate all that in one plugin. So what if we do have one interface? If we do have one interface, we can address all these runtimes with a single plugin in the engine. The developer no longer has to pick and choose which plugins it enables and which plugins it disables. And the developer's game will also be forward compatible with runtimes we don't even know about yet. One complaint I often hear, though, about open standards is that because they're made by consensus in a group, they move too slowly. And the standard would impede progress within the VR market. But there is a concept within OpenXR called vendor extensions, where a developer can add new features to the specification without having to go through the group and without having to wait until a consensus is reached. So let's look a bit at the incompatibilities that OpenXR is addressing. So the biggest sources we've identified is runtime selection, which is about which runtime am I going to use. An Oculus Rift user might have both the Oculus runtime and the SteamVR runtime installed. And which one to use is currently up to the engine. There's input mapping. How are all the in-game actions bound to the controller? And lastly, there's frame blocking, which is mostly a rendering performance thing, where different runtimes perform differently because they behave differently for blocking. So let's look at runtime selection first. The current way that UE4 handles this is that there's an internal priority list, where more native runtimes are at the top and more non-native runtimes at the bottom. But we don't actually know which runtime the user prefers. we just make some decisions about this priority list, and if a vendor adds a new plugin to UE4, they tend to want to put their plugin at the top of the priority list. So how do we handle this? With so many runtimes, if the user were to select the default runtime, it will have to be the default for the entire system. So the user will get to decide which default this is. The developer will only have to enable a single plugin in the engine, and the OpenXR will determine what runtime to actually use. The engine will work with any conformant runtime. So if you keep to XR best practices, you won't have to worry about which runtime actually ends up being used. So how does this work? Instead of using that priority list, the OpenXR engine now delegates runtime selection to the OpenXR loader, which is an open source library that will ship with the engine. And that library is responsible for actually looking at the system, determining which runtimes are installed, determining which default the user has selected, and then loading the correct runtime. This library is not actually present on the system itself, so the engine is responsible for updating it. So how does the user select an active runtime? Here's an example from the Windows Mixed Reality runtime. There's a single button which the user can set this runtime as the active runtime if it is not already the active runtime. Each vendor will have their own settings panel for this, and vendors have been instructed to only change the default if the user has explicitly indicated that they want to change it. We are all honor-bound to play nicely with each other, and we don't want to repeat the priority list. So let's look at input mapping. For OpenXR, rebindable actions have become a core concept. If you're already familiar with UE4 development, you've already encountered actions once because you have to configure input by defining actions and then suggesting bindings for them. But if you're not familiar with UE4 development, here's a quick crash course on what actions are. So there are two ways to handle input when you're in your game. You can either define the combination of keys that need to be pressed to trigger an in-game event and define those directly in your game logic, but this would make rebinding incredibly difficult. So instead of defining these physical buttons, we can instead define the action that the user wants to do in the game. So in this example, we have the user who wants to teleport. So instead of defining the physical button for teleportation, we simply check if the teleportation action has been triggered. Now, to actually use these actions, they have to be bound to a physical button. So how this happens in OpenXR is that the developer will bind these different actions to different buttons defined in what we call an interaction profile. So what an interaction profile is it's basically a description of a physical controller. In the case of the Oculus Touch, we have the X and Y button, the thumbstick, etc. And we define these directly in their interaction profile. So the runtime will then map these physical buttons to the actions based on the bindings that the developer suggests. However, the runtime is not enforced to use the bindings the developer has suggested. There might be different bindings defined by the user, as we've seen in Steam VR input, for example. Or, in the case of an entirely different controller, the runtime is allowed to emulate an Oculus Touch controller using, for example, Valve Index controllers, if that makes sense, and if that's the only interaction profile the developer has supported in their game. This is an important concept because we might want to run games on controllers that have not even been released when the game was developed. So here's an overview of all the different profiles that have been defined in the specification. You're encouraged to provide bindings for as many of them as you can, but only provide bindings for the ones you can actually playtest. The emulation will only work if you have only provided bindings for the interaction profile that you've playtested with. If you try and just guess at it, then the runtime will use your best guess, and that may actually be worse than what it could find out on its own. in the end, we want to know which profiles you've designed your game for. So let's look at how all this works under the hood. So you have a physical button that's being pressed, and the physical button is described in the interaction profile using a URL-like path. So the runtime takes this path, it looks it up in the table of suggested bindings, and in this case, we have the A button that's being clicked, and in the suggested bindings, we have a click event that should trigger teleportation. So in the game, it will then trigger the teleportation action, and the game logic will take over from there. Currently, these URL-like paths are exposed in the plugin, but we want to abstract away from this as soon as possible because they're quite inconvenient to handle. So how does the OpenXR plugin in UE4 actually look like right now? First, some history on the OpenXR plugin. It was first added as an experimental plugin in UE4.22. It used the provisional specification and wasn't very stable at that moment. And we since updated it to the final release of OpenXR in UE4.23, and we're continuing to improve it from there. So let's look at how input is handled in the plugin. Currently, you have a separate input panel where you define all your supported interaction profiles and suggest bindings for them. In this separate settings page, you bind physical buttons to motion controller keys and then bind those motion controller keys to your actions in the regular input panel. Some helpful defaults are given, but they're incomplete because motion controller keys don't cover all the different keys on all the different controllers. Now, this can be quite intimidating and inconvenient because the configuration here is split across 2 pages. So, can we do better? We can, but we'll need to make a drastic change. We will need to deprecate motion controller keys altogether, and this is the most important takeaway from the presentation. Instead of these motion controller keys, we'll define the physical keys from the interaction profiles. So let's look at how that works. So let's look at the current situation. The current situation is that we have a bunch of different plugins that all share some of the keys as motion controller keys, and then define a couple of their own. In this case, SteamVR defines a trackpad because the trackpad's not part of the motion controller keys, and Oculus Touch defines their CapSense sensors. Now, this, at first glance, this looks like a good idea because we want to provide as much cross-device compatibility as possible. So defining a common subset of motion controller keys seems to make sense. But if you look at what the motion controller actually defines, face button 1 and face button 2 isn't exactly descriptive of what the developer intended to bind to. These face buttons can be bound to entirely different buttons based on the controller. So what do we get if we take motion controller keys away? So if we take motion controller keys away, we define the physical controller and each button on the physical controller. This way, we don't lose any of the information by using generic face buttons. We know exactly which button you target. And we also don't really lose the abstraction capability for motion controller keys because even though we define the physical buttons, we're allowed to emulate them on any other controller. So we don't really lose anything to removing motion controller keys, and we just increase clarity. So let's look a little bit at the plugin implementation. This isn't exactly necessary if you're only using the plugin to ship your game, but it's always helpful to know a little bit about how it works under the hood. So the architecture of the plugin consists of 2 modules. There's the OpenXR module, which handles all the rendering and tracking. And then there's the render, it has the RenderBridge class and the SwapChain class. So the RenderBridge class is responsible for abstracting between the different graphics KPIs. And the SwapChain is responsible for managing the render targets. And then there's the OpenXR input module, which has a class for controller just to detect which controllers are currently active. and it has the collection of actions that you defined on which it generates suggested bindings. So let's look at the current supported extensions in the plugin. We've got 4 extensions at the top that are needed for supporting the various graphics APIs. And we've got a few more extensions. There's a composition layer depth extension to help with reprojection, visibility mask to help with performance, and the first vendor extension from Varjo to assist with their hybrid headset. So let's look at the final point of incompatibility, which is frame blocking. Now, frame blocking is a technique to reduce latency by simulating the frame as close as possible as to when we're actually going to render it. There are different approaches to your pipeline, and frame blocking affects them differently. So let's look at the simplest pipeline design first. If you have a regular pipeline, you just have a loop. You first wait until the frame is unblocked. Then you simulate that frame, you render it, and you submit it to the headset. In this case, simulation needs to happen as quickly as possible because we don't want to wait too long with rendering. But simulation doesn't actually have that many elements that are actually sensitive to latency. So there's a different pipeline design. So we could also make a deep pipeline. So with a deep pipeline, we first wait until the frame is unblocked. Then we simulate the next frame while also simultaneously rendering the latest simulation that we have. To prevent latency issues, we do what we call a late update, which updates things like the headset and the controllers, which are actually sensitive to latency, and makes sure that they are updated to the latest tracking data we have. So let's look at the roadmap for the plugin. As explained before, we're going to simplify giving suggested bindings. We don't want you to have to go through 2 settings pages every time. The plugin itself will remain experimental until all runtimes are conformant. OpenXR is currently in the process of defining conformance tests for their runtimes. And as long as we don't have conformance tests, we can't be sure yet whether all runtimes will behave the same. So existing partner plugins, like the Oculus plugin or the SteamVR plugin, will remain supported. We're not going to remove support for those. But we will try and move some code to OpenXR, and some changes in OpenXR might affect those plugins. However, new partners that want to add plugins to UE4 are encouraged to instead use OpenXR so that we don't exacerbate the problem of having countless plugins in the engine. And thank you for your attention. That's all I wanted to talk about OpenXR today. But if you have any other questions, I'm available in the speaker pavilion to answer any of them. Thank you very much.